Good day, everyone. My name is Emil. I'm a solutions architect with Neo4j based in Sydney, Australia. And we have with me my friend Ajmal. Ajmal, do you want to introduce yourself?
Yep. Hi, everybody. My name is Ajmal. I'm a solutions architect at Databricks based out of Melbourne, Australia.
Cool. So for today, we will be talking about how does a combined reference architecture look like with Neo4j and Databricks. I remember we were having a chat a few months ago where we're talking about our customers and prospects and data professional asking how Neo4j integrates with Databricks. At the same time, vice versa, how Databricks addresses the need for graph using Neo4j. And then we saw an opportunity in Nodes 2022. It's coming up where we put our session up, hoping that our session will get selected, and now we're here. So if we move on to the next slide. So in this agenda, we just kept it light. We'll start with an overview of Neo4j and Databricks as a company. Then we'll talk through about connected data lakehouse architecture. What are the key strengths of Neo4j and Databricks that when leveraging those two technologies together will generate actionable insights at the same time will be valuable for technical and business users. And finally, we'll wrap up our session with a demonstration using a supply chain data. This is at the back of the blog that Zach Blumenfeld released a few months ago to showcase how Neo4j and Databricks can help productionize a machine learning model. Because remember that around 80% of machine learning projects fail to go to production, right? So the need for operationalizing it and making the most out of it is quite critical. So we'll go through who is Neo4j and Databricks. Neo4j, we are the connected data company, and we have the industry's largest dedicated investment in graph. And we are the category creator of labeled property graph, the first enterprise graph data science platform in the market that provides the most flexible graph data model. At the same time, we built an open source Cypher query language, which is most of the basis for graph query language and upcoming database standards that will be released in the coming years. So we are based out of Silicon Valley at the same time with in Malmo and work with thousands of organizations across the globe, from financial services, telecommunications, software vendors across several verticals here in Asia Pacific and across the globe. Within Neo4j, as a great graph data platform, right, at the heart of it, we have the database that can perform both analytical and transactional workload. At the same time, we are cloud agnostic. We are available in AWS, Azure, and GCP, or even on-premise if required. That allows to cater for several end users, data scientists, engineer, business stakeholders, operations manager, etc. Right. At the back of that, we have a data science and analytics capability. That's a graph data science that allows you to execute graph data science algorithms to answer different types of questions, segmentation, finding bottlenecks in the context of supply chain, and so on. And then it allows you to interface with several integrations via REST API, or even with your favorite visualization tools, or like Power BI, Tableau, or even with Neo4j Bloom, which are native graph visualization available out of the box. Then we have with us my friend from Databricks.
Awesome. I'll give everybody a really quick and brief overview of Databricks. So Databricks is the Lakehouse company. We were the original inventors and pioneers of this category called the data lakehouse. And as a consequence of this, as well as recent developments, we've been recognized by Gartner as being leaders in both the database management systems Magic Quadrant, as well as the data science and machine learning platforms Magic Quadrant as well. And we'll go through a little bit of a very quick double click on what the Lakehouse actually is. But we were the original creators and inventors of massively popular open source tools and frameworks. So for example, Delta Lake, Apache Spark, as well as MLflow. We've raised over $3 billion of investment to date, with over 4,500 employees across the globe, servicing over 7,000 customers, ranging from very small startups to tech unicorns, all the way to Fortune 500 companies that are listed on stock exchanges. So we span quite a big breadth, and I'll double click very quickly on what the Lakehouse is. So this Lakehouse platform idea really has to do with unification and simplification. It comes from this notion that you don't necessarily need to have siloed development stacks for your data warehousing, business intelligence, engineering, streaming, as well as data science and machine learning use cases. Essentially, it unifies a single place, which we call the Lakehouse platform, for all of these different personas to come together to develop and build data products within a single unified location. What we do then is have a platform that is underpinned by technologies that are open source. So for example, Delta, that applies data reliability and performance irrespective of the use case or the end consumer of that data, as well as fine-grained governance on top of files and folders using this technology called Unity Catalog, which has been a complete game changer for organizations, that also allows you to see lineage. So whether you're building SQL dashboards and doing warehousing or building machine learning models, you're able to see end-to-end lineage and governance on top of your data assets. And very similar to Neo4j, we sit across all three of the major public clouds. So the same unified experience that you have building data products is similar across all three of the major public clouds. Mm-hmm. And this introduces a significant level of simplicity because the unification element of it, faster time to value, multi-cloud, so you're not necessarily locked in, and open. Open in the sense that Delta Lake is a completely open source file format, so you're not going to be locked into a vendor if you're using this product, which is quite important. So what we're going to go through today is this connected data lakehouse concept. And Emil and I have termed it, and we really hope that this term sticks. So Emil is going to talk really quickly about the benefits and features that Neo4j brings, and I'll talk about the Databricks benefits. Emil?
Awesome. So I think just to give you an idea, so Connected Data Lake is born on the idea that Neo4j is the connected data company, and Databricks is the data lakehouse company, right? Combining those two provides a lot of synergy between those two technologies that enables organizations to source, collect, and curate the data in Databricks Lakehouse, connect using Neo4j, and together we generate actionable insights and tangible value to make an informed decision, right? Talking of Neo4j strengths, right, we can summarize it into three. One is the ability to data model and store complex connections and interdependency, putting relationship as first class. By having those data interconnected and those complex relationships being shown and stored or persisted in the graph database, then it's a breeze or ease in traversing those data that then reduces the time to generate those insights. Right? And having those data stored as a knowledge graph in the database enables you to efficiently execute graph data science workload on top of your knowledge graph, like finding similarities, interdependencies, bottlenecks, or even segmenting your network into groups or clusters.
And from the Databricks side, I included just a couple of really quick talking points. So for example, the real demo that we're going to go through today talks about the productionization element of it. And in order to be able to productionize, you need to be able to scale, execute workflows in a consistent and governed manner. So I listed workflows as being a key capability within our architecture. Secondly, managed ML flow allows for the simplification of training, building, testing, experimenting, tracking of machine learning models, all the way from essentially hitting .fit to productionization and having a model registry where you're really able to govern the machine learning model across the various lifecycle stages, and then also be able to see if there's things like drift that occur as well. And then lastly, I listed out this Lakehouse architecture just as a catch-all where we're able to merge and essentially deal with batch and streaming workloads in a unified architecture, which is a massive game changer because you're not necessarily forced to venture outside of this single platform when you start needing to deal with either batch or streaming. And also, we also have the ability to deal with semi-structured, structured, and unstructured data as well within this platform. So here is our overall sort of architecture, and it's very catered towards that cargo use case for the supply chain where we're trying to essentially predict delays across routes within the supply chain. So very similar to what Neo4j does, it's a similar experience across all three major public clouds. So we envisage that raw data will land in cloud object storage. So on AWS, this would be S3. On Azure, it would be ADLS, and GCS on GCP. So once raw data lands within this directory, and we envisage that this will potentially come from like ERP systems or streaming sources, or essentially any place where you have like raw data coming from the supply chain. Once it lands, we use this technology called autoloader, which incrementally ingests new data as it lands into that S3 bucket, for example. Then using Spark Structure Streaming under the hood, autoloader essentially ingests that data into the Lakehouse, where we then take that data, apply some transformations to it to go through a refinement process, and then pump data to the connected data Lakehouse, to the connected data in Neo4j. And then we utilize those graph-specific features from Neo4j's Graph Data Science library to be able to train and build machine learning models on Databricks. And therefore, what we've done is we've taken really some interesting like key benefits from both the Neo4j and the Databricks side that lead to higher business value. So we're able to then visualize the underlying graph structure that the cargo dataset contains, what the supply chain dataset contains, using Neo4j. But we're also, on the flip side, able to productionize an end-to-end machine learning model that utilizes data all the way from like source systems to inference that predicts whether or not a specific delay is going to occur across a route. And so really you have a really interesting interplay between both structured data in tabular format and graphical data that have essentially better benefits for building and training and deploying machine learning models as well. So all of the orchestration, I will demonstrate shortly using our workflows capability. And we hopefully hope that this leads to like greater value generation and ideas for companies that have supply chain data sets. Really quickly, I wanted to touch upon the machine learning capabilities because I know we sort of just put like a bit of box around it. But what we see is for machine learning, really three key steps, right? Data preparation and data ops, where we've essentially brought in this feature store concept. And Emil and I, when building this demo, heavily made use of the feature store. We're able to essentially persist the features that Neo4j calculates as well as Databricks calculates to this feature store so that when the model essentially is called, you don't necessarily need to recalculate these. They are done for you on the fly, and that mitigates quite a bit of online and offline skew, which I'll touch upon shortly. Now, the integration to Unity Catalog with Feature Store means that we have end-to-end lineage of where the features came from. So if the features essentially degrade over time, we're able to trace where and why. And other data scientists within the supply chain organization, whichever organization that uses this, is able to then see the features that we utilized and how we got better performance. Now, when we were ready to essentially build machine learning models, we had two key choices. We were able to use either notebooks or an AutoML capability in the Databricks platform. We chose the notebooks because we wanted to be able to build code and utilize essentially API calls to Neo4j as well. So we were able to heavily use MLflow there as well. And then lastly, what we did was we deployed a real-time inference API of our machine learning model that predicts delays. And that serverless real-time inference essentially is able to scale up and scale down as the data needs grow for the organization. All of this entire process end-to-end is heavily utilizing a managed MLflow offering. And MLflow already is a massively popular online library that has over 10 million monthly plus downloads. Now, I'll really quickly touch upon that feature store because I think it's quite important. The feature store essentially solves for two fundamental problems. The first is discoverability and really reducing essentially reduplicating work. Data scientists can essentially go to the feature store and see if other data scientists within an organization had calculated a feature. So for example, average session time. So they don't necessarily need to recreate the wheel every time they want to build new models. They can use the models or the features, that other data scientists have used. And what this feature store also does is provide for you this level of traceability. So you're able to see what models are utilizing what features. You're able to see what the producers of those features were and how often they're refreshed. And then lastly, the second problem that the feature store solves for is the online and offline skew problem, where machine learning models fail silently. And if there's different types, if something different occurs to when you trained the model to when you're actually serving the model in terms of the actual underlying data sets, you essentially have skew between online and offline. And what the feature store does is it recreates those transformations for you so you don't necessarily have to worry about that as well on the online serving side of things. Now, I also mentioned the serverless real-time endpoints piece. We spun up an endpoint that has our model serialized across it. And that endpoint essentially can be interacted with using an API with an invocation. So we're able to essentially call that API with a specific route. So for example, if we were doing supply chain planning and we had a bunch of different routes that we wanted to check whether or not there would be a delay, we can essentially hit this API. It essentially calculates, retrieves the features for the model. So for example, the closest centrality features that Emil is going to touch upon, recalculates them, and then predicts for us whether there's going to be a delay. And this really is production grade. So we're able to scale. It's got high availability and SLAs and auto scaling and observability as well. So we can see if our API has degraded over time. So Emil's going to touch upon the graph data science framework that we used.
Yep. So Graph Data Science Framework is a toolbox that enables and combines the power of native graph analytics workspace and database with scalable graph algorithms and visualization. So that users can reliably and provide a better experience in the ease of use, right? So this is at the back of the reference architecture that we've shown a while ago, where we collect the data, we use Graph Data Science, and then we serve those data via visualizations and APIs. So that's basically at the back of that, right? And Neo4j, Graph Data Science Toolbox is comprised of these three major features, right? So you have at the center of it the database, a highly scalable native graph database, purpose-built to persist and exploit those relationships. And then on the left side, we have Neo4j Graph Data Science Library, which is a toolkit with flexible data structure that allows you to project a subgraph of what you've stored or persisted in the graph database and enables you to execute powerful graph algorithms, centrality, segmentation, similarity, just to name a few. And then to cap things off, we have Neo4j Bloom, a graph visualization and exploration tool that allows you to visualize those result of the algorithms, find patterns using codeless search. And all of that will be shown to you in the coming parts of the session. All right. And then to illustrate the end-to-end data flow, we have stored the data in one of the cloud blob storage service. So you can store it in AWS S3, Azure Storage Account, or Google Cloud Storage. Once the new data arrives in the bucket, Databricks Autoloader detects the new data set that will then be ingested into the bronze layer. So for anyone who's not yet familiar with the Lakehouse architecture, what is a bronze layer? Bronze layer is the raw ingestion layer where you're sourcing data from several sources. RDBMS, JSON, flat files, and just to name a few. And then the data will be filtered, refined, joined by metadata to produce a silver table, right? So that's the refined layer. Afterwards, data will be curated in the gold layer. What we did is we extended the architecture to have a connected goal. Connected goal where we connect the most important data required for analyzing complex relationships. Let's say, for example, you have a problem of determining a bottleneck in your supply chain or segmenting your logistic warehouse based on their interdependence and connectivity. Both of those gold layers, the connected gold and the gold layer from the Lakehouse architecture, will complement each other. That will be used in training a machine learning model. At the same time, we use this to visualize the data either as a graph using Neo4j Bloom or in any of your favorite dashboard in tabular form.
Awesome. And this connected gold that Emil sort of alluded to is then used as features for our machine learning model. When we were building the machine learning model, we essentially utilized, again, like I mentioned heavily, the ML flow or the managed ML flow within the platform. We're able to track parameters, artifacts, as well as the actual model itself across its various lifecycle stages from staging to production. We were then faced with multiple different deployment options, and we'll show you how we used batch inference for a bunch of new data on the trained machine learning model. We can either use also a REST API. We also have monitoring built in. But the key difference, again, was that we actually persisted the connected gold data into the Databricks feature store so we could have ultra-fast feature lookups on the fly when we serve the machine learning model to our end users. Now, Emil's going to go through the Cargo 2000 dataset. I'll show what that actually looks like essentially on the Databricks side, and Emil will show what it looks like on the Neo4j side. And I'll pass it over to Emil to introduce the overall dataset.
Yep. So the dataset shows like a business process of transportation or logistics, right? It represents how a freight forwarding company in which up to three smaller shipments from supplier are consolidated and then in turn shipped together to customers. The business process is then structured into incoming and outgoing transport legs, which jointly aim to ensure that the freight is timely delivered to the customer. And these are just some of the parts of the business process. So we have the freight reception, and then afterwards it goes through a freight departure, and then it goes through a freight transfer or arrival, depending on where it's at in the supply chain value chain, and then we have the freight delivered to the destination. And then if we model this flow into a knowledge graph, this is how it looks like end to end. So you have your entry point, a departure, warehouse, and then up until it reaches the destination. And all of that points out to a location somewhere in one of the airports that we have in the data set. So now AJ will demonstrate to you the end-to-end data flow and how it looks like and how we ensure that we'll be able to integrate with between Neo4j and Databricks.
Awesome. Thanks, Emil. So Emil and I built a workflow that essentially does this. And really quickly, for those who aren't familiar, this is what a Databricks workspace looks like. And there are 3 key personas available to you with separate tools depending on the persona that you choose. We're in the machine learning persona, so we have access to experiments, feature store, and models, which we're going to touch upon. But really key here is that we utilized a workflow to be able to essentially outline all of the processes that we went through to build this use case. It starts off with ingestion, utilizing that autoloader capability that I mentioned. We then have a process that ingests the data to Neo4j. We then essentially calculate a bunch of graph level features and persist them to our feature store. We then perform some very simple modeling where we try to predict delays using a random forest. And then we use MLflow to be able to register that model. And then we have a batch scoring script that essentially has some new data that it essentially batch scores using the trained model and the persisted model in the registry. Now, this workflow is quite important, particularly when you go to the productionization setting, right? You want this to be Git controlled, you want this to be scheduled, and you want this to be fault tolerant as well, and you want to control the compute that goes behind this. So Databricks provides a runtime with over 50 managed libraries for you that mitigate dependency issues with respect to like different packages. And so we used a cluster, and the same cluster is applied to all of the separate steps within our workflow. Now, I'm going to go through each one of these notebooks and briefly just touch upon 1 or 2 key points in each one of these. But Emil and I will make the whole code available to everybody as well on GitHub. So the first thing that we do is ingest data from object storage. Now, the key thing to note here is that when we're reading, when we use autoloader, we use the cloud files format when we do Spark read stream, and we essentially pass a directory path so that this directory path is watched for every single time autoloader spins up to ingest new data that has landed from our supply chain cargo data set. It will only essentially ingest the new data that has landed. And it does that through checkpointing, and it's a couple of other value adds, which I could link through after the call. But we essentially take that new data and stream that data directly into a table. And for the purposes of demonstration, I called it bronze cargo table because we see this as being the first place that data is ingested into our end-to-end process. So this is very raw data. Now, if I select star from that table, these notebooks are polyglot, so I can essentially use SQL, Python, Scala, or R. I use SQL to be able to just have a look very quickly at the overall data set. And as you can tell, it is quite messy, right? Because there's question marks, numbers, and everything's mixed together with relatively not a lot of information. So we went through a process to be able to append information to that overall table. And we then go to our data explorer, and this data explorer shows us the different databases and tables within the actual workspace. The key thing to note here is that all of the underlying data sits in files and object storage. So for example, S3, but I'm able to interact with these tables like as if they sit within a database. So I have a database called nodes_demo. nodes demo contains a table called bronze cargo table, and each one of these columns within this bronze cargo table contains commentary that we retrieved from the internet for this actual specific data set. What's really cool about this commentary is that Databricks will then index this, so we have discoverability of what each one of these columns mean, and metadata discoverability as well. Now, the thing to note here is that even with the metadata sort of appended to this data set, it's very difficult to be able to read this data based on the way that it's laid out. And that has to do with the circular loops that Emil showed. And so this really motivates the need for using Neo4j so that you can actually see what the actual underlying data set is rather than interacting with it in a tabular format, which is quite difficult to ingest, at least from my perspective. We then go to our second notebook, which Emil wrote a Spark a function that utilizes the Spark connector for Neo4j to be able to send data to Neo4j. So again, this is really distributed, right? We can use Spark, we have parallelism, we have clusters, and we're able to send data to Neo4j in a UDF that Emil wrote. And this code will be available to everybody as well. Emil will very quickly touch upon the graph features that we used in our third notebook.
Yeah, so just quickly, in terms of how we crafted the graph features, we used the Graph Data Science Python library, right, to be able to project a subgraph of our supply chain network and then execute some of the features that enables us to measure operational load using degree centrality, flow control using betweenness centrality, transitive influence in the supply chain network using eigenvector centrality, and even segmenting your network into its regional interdependence using Louvain community detection algorithms. And then out of that, we generated those files, persisted it into Neo4j, and then from there, AJ, you want to talk about how it's stored into the Databricks feature store?
Yeah, absolutely. So after the graph specific features have been calculated, and they're typically done on like a route by route basis. So you have like, airport A, airport B, we have log betweenness, log in degree. But what we also did was we did a window function calculation that essentially just has a rolling delay per route or shipment ID, sorry. And so that's just a separate feature that's calculated. And then after we do that, we have the final column, which tells us whether or not the actual route was delayed or not. So we then persist that feature that feature table into our feature store, and we need to pass primary keys. So we use the shipment ID and the airport primary key, as well as the description for this feature store, so that if other people want to see what this feature table actually describes, they're able to utilize this description field to be able to do that. Then we moved on to some machine learning. We were able to essentially use a feature lookup to, again, retrieve the feature table. We then built a very simple random forest classifier, but the key thing to call out, aside from the ML flow integration here and sklearn, is that we used fs.log_model, which essentially means, which tells ML flow that, hey, this model has actually been packaged with a feature table so that during inference, that's actually taken care of for us, whether it's batch or real-time inference. So I'll really quickly show you what the tracking server looks like. So as Emil and I were building these models, we were able to then go in and see what these models actually look like under the hood, as well as metrics as well. This really helps with experimentation, right? And as you can see, MLflow is baked into the platform as well. So if I just deep dive really quickly on one of these runs, you're able to see a bunch of parameters that we used. You're able to see metrics, and you're also able to see some charts that we decided to include. So for example, the confusion matrix. And our model actually did quite well, but we weren't really testing for performance here in terms of model accuracy. The key thing to call out here really quickly is that MLflow integrates with Delta, and the Delta file format contains version histories of the actual data. So we're able to see exactly what version of the data created what model as well. For traceability, that's quite important. So then we moved on to the model registry. So we promoted that model to our model registry because we were happy with it. And as you can see, there's various versions of this model. Version 3 is in staging, version 4 is in production. And what we did was you can essentially just have one-click deployment for inference, but we wanted to show you score batch. So it's able to utilize the production version of this model. And with a couple of inputs that I've shown here, the feature store table essentially pulls in the rest of the features. We're able to then utilize those features as well as the actual keys that we used to be able to build this prediction column for our machine learning model. So that's just batch inference. You're also able to use real-time serving inference. So here's an example where we show an example, send a request, get a couple of results out, and we also track actual usage as well as other metrics for your serverless real-time endpoint as well. Really quickly, just wanted to show you the feature store too. So here is the description that I mentioned earlier, as well as the actual columns of the features, what models are utilizing that. So version 4 is utilizing it, what jobs, where did it actually emerge, and here is the actual consumer for that score batch that I mentioned earlier. And then the last thing I wanted to show before I hand back to Emil is that although you're also able to visualize the underlying graph structure, you can still utilize a SQL first persona to just essentially use like select statements against the underlying table too. So here we're using total delays and we're just pulling that out. I'll pass it back to Emil now to conclude.
No worries. Adish, can you? Yeah, thanks so much. Yeah, so this is just a summary, quick summary of the Databricks or the feature store, the Databricks feature store. So we have these different features and where it's originating from. So as mentioned, we have the rolling delay average, which is like the historical rolling delay average originating or crafted within Databricks. And then some of the network or graph features are done or built within Neo4j. So for example, degree centrality to measure the operational load of supply chain, which essentially means finding if it needs more resource to run effectively, or between the centrality to find bottlenecks, eigenvector centrality to find the downstream effect of a bottleneck, and at the same time grouping those into Louvain community detection. Right, and all of that we have the code snippet available, and we'll be publishing this slide as well. And just quickly, in terms of how we consolidate all of those data, the degree centrality and all the graph features so that we can integrate it within Databricks. So this is just an example of the Cypher query that we use, wherein we're fetching essentially the different airport IDs, right? And its corresponding graph features, degree centrality, betweenness, eigenvector, as well as Louvain. And then this is then piped into Databricks feature store, which we'll then use for the machine learning model. And to wrap things up, right, so how does it look like in terms of visualizing it using Neo4j Blue? Right, so this is just an example of showing a path of shipment number 12, right? So imagine you have a shipment which originates from two locations, Rodriguez side and Shanford. It went through several transport leg until it reaches a transfer point at Elisaville, and then from Elisaville, it then moved and delivered into Waytown, right? And supply chain, the nature of the supply chain industry being a connected data makes sense for it to be visualized as a graph and complemented with Databricks to be able to enrich those data and performs those transformation, data cleansing, and all other ETL activities. All right. I think that's pretty much it for our presentation. I'm not sure if we still have time to do a Q&A. Could probably have one or two. I'll take the first one, which is like, what does ease of traversal means? Ease of traversal means having the data already pre-connected, right, in the graph database, which means being able to pull that out much faster to generate those insights if you have all of those data pre-connected, especially if the nature of the problem that you're solving is highly complex in terms of relationship and interdependencies. I think, Ajmal, there's also a question of why. Yeah.
Oh, no, I was just going to say really quickly that there's a couple of questions on the GitHub link. Emil and I will publish that after this talk.
Yeah.
And I think, Emil, you were going to ask me about that connected data lakehouse question.
Yeah, that's not connected. There's this one question on whether data lakehouse replaces a warehouse, data warehouse.
Yeah, so within like, we believe yes, particularly when it comes to, that's a better way of looking at it. You don't really need a data warehouse, right? They're very expensive, have lock-in. They do have use cases for like OLTP. So if you want to power a website, yeah, definitely have a data warehouse. But when it comes to OLAP, the Lakehouse is the best place to perform those queries. You can scale it, have support for structured, semi-structured, and unstructured. And with Databricks, all the data stays within your cloud environment. We've also done a bunch of benchmarks showcasing the Lakehouse versus traditional data warehouses for cost and performance. You can find those on the Databricks Lakehouse, the Databricks website for the performance comparisons.
Cool. I think that's yeah. That's all for our presentation. So for all other questions, we'll just answer it individually. Yeah. Thank you.
Thanks, everybody.